The expansion of the universe is pushing everything away, but gravity wants to pull everything back, decelerating expansion. But we measure an accelerating universe. So that means there's something pushing back, and we call that dark energy. We're going to talk all about it today on Non-Expanding. Dark energy. Do we need it? Is it real? The standard model of cosmology is called lambda CDM, and that upside down V is the lambda, and that represents dark energy. The CDM stands for cold dark matter, but don't get dark energy and dark matter confused. They're different, and this is about dark energy. Hubble's constant is the expansion rate. Although it's not actually constant, it's the current value of Hubble's parameter, and that changes over time. You may think that an accelerating universe means Hubble's constant is increasing, and that's a good guess, but it's actually decreasing. Let's consider a special case where Hubble's constant is constant, and that gives us a linear relationship between redshift z and distance d. This is an exponentially expanding universe, also called a de Sitter universe or a pure dark energy universe. If the expansion rate were higher, the slope of this line would be lower because you get more redshift with your distance. So lower slope means more expansion. And if the expansion rate were lower, then the slope would be higher because you need more distance to get that redshift. So I said this is a special case. This is only true, this linear relationship, with these particular parameters. So let's talk more about them. They are how much of the universe is dark energy and how much is matter. That horseshoe symbol is omega. So we have omega lambda and omega m. A universe without dark energy and only matter is this green line. And we see here that because redshift z equals 0 is the present, that in the past, this lower slope means there was more expansion, and that expansion has decelerated. Unfortunately, this model does not fit the data we have. This is the supernova data, and this is their time dilation measured in z. So the green line is too low for the high redshifts and too high for the low redshifts, depending on which value of Hubble's constant you use. A universe with dark energy, about 70% dark energy, if that sounds familiar, does make a good fit for the data. Therefore, dark energy must exist. We can see with our own eyes the data needs dark energy. Now, you could also see that it might look like this is also a decelerating universe, just like the matter-only model. So let's see them side by side. If you take the slope of this green line, and that's this red line here, you can see a little bit of a different picture emerging. If you take the slope of the red line, you get this blue line, and then we see this little dip. This is the acceleration happening right here. The universe is changing course. And since z equals 0 is the present, it means this change of course has happened really recently. So congratulations, universe. You've hit a milestone. But what actually is happening here? Well, when the universe expands, the matter in it stays the same. So if the volume goes up by the power of 3, then the density goes down by the power of 3. But under expansion, dark energy doesn't really change. It's just cool like that. So eventually, the expansion of space lowers the density of matter, weakening the pull of gravity, but not changing the dark energy density, and that takes over, and then you have an accelerating universe. The math looks a little complicated, but it's really just these three things added together. We haven't talked about omega r, and that's the density of photons. And that changes by the power of 4 because it changes with volume like matter does, but it also redshifts. But it's also really small, so it isn't talked about as much. Matter changes with volume, like we said. So at a redshift of z equals 1, the distances are half what their current distances are. So in 3 dimensions, that means the matter density was 2 to the 3, 8 times higher. But dark energy, it's still the same because it's cool like that. So far, we've talked about the standard model of cosmology, its parameters, and that it needs dark energy to fit the supernova data. Gravity decelerates expansion, and dark energy accelerates expansion, and we saw the mathematics as to how dark energy comes to dominate. So, with all of that said, is any of this real? Well, if expansion is pushing out and gravity's pulling in, but we don't measure deceleration, we measure acceleration, what if instead of discovering dark energy, we discovered that gravity doesn't decelerate expansion? Consider the null hypothesis. There is no relationship between the measured redshifts, or time dilation, and gravity. Lambda CDM is what's known as an FLRW model named after these fellas, and this is based on general relativity, which is a theory of gravity. So let's assume that cosmic redshift and time dilation are unrelated to gravity. What's the data really telling us? Well, each dot is a supernova, and its z is its time dilation, how much its time is measured to be stretched out. Taken literally, we could say that time is running slower at these distances and redshifts. Let's say time runs at 1 plus z. Integrating 1 over 1 plus z gives this log function, and this is the time-dilated past hypothesis, a non-expanding model introduced in the last episode. Compared to the lambda CDM, it only has one parameter, and that's just a pure constant. And lambda CDM needs dark energy to fit the data, but the time-dilated past hypothesis doesn't. So, the most literal interpretation of the evidence says that time ran slower in the past, space isn't expanding, there is no such thing as dark energy, and you should comment and subscribe. Thanks so much for listening.